Lechatliers principle. If you do a chemical reaction and you stress the chemical system, the system will react to relieve the stress. And what I mean by stress is if you add more reactants or products, change the pressure, change the temperature, the system, the chemical system or the chemical reaction is going to try to counterbalance the stress that you have added or subtracted by shifting the equilibrium to a point where you're either going to be making more products, making more reactants, or some other factor. Okay, so let's see how Lechatliers' equilibrium principle works in a dynamically stable equilibrium situation. So remember, in this case here, we have reactants, and let's see what they are. Those are reactants here. Here are my reactants. So all of these are reactants, and then again we have products. And here are my products. So let's see what happens when we actually do a stress on a system. So now consider this at equilibrium right here. This is all equilibrium. What happens when we stress this side of the reactants? So in other words, we're going to add more reactants. So let's do that. Let's add more reactants. And so we're going to push down. In other words, when we go down, we're going to say we're adding more reactants. So I'm adding more reactants onto that side, which makes it heavier. I'm adding more reactants. So I've got more reactants now at equilibrium, or now it's no longer at equilibrium, so I'm pushing down on that side. And what happens is we need to now counterbalance it by either A, getting rid of the reactants, either pulling them off the thing, but since we've added them, they're going to have to now be converted to products. So what happens is the reaction shifts towards the products. So we add more reactants. We add more reactants here, and now the shift is towards the products. So when we do this, we add to the left, we shift to the right. Add to the left, shift to the right. Add to the left, shift to the right. Okay? Now let's say instead of adding more reactants, we actually add more products. So let's say we add more products. So this time we're going to make this side get heavier. We're adding more here at equilibrium. So when we add more than we normally have at equilibrium, we're going to push down on that side. And remember now, again, the only way to get rid of that products is we have to convert the products back into reactants. So now we're going to shift this way. So we're going to shift, if we add to the right, we shift to the left. Add to the right, shift to the left. So here we are, we're adding to the right here, and we're shifting to the left. Adding to the right, shift to the left. Okay? Well, not all the time are we adding stuff. Sometimes we're removing material. And when we remove material, sometimes it's done to help the reaction go to completion. If you do reaction A, let's say you do a reaction, and normally the equilibrium is about 60% of the material is products and about 40% of the material is leftover reactants. And let's say you want to make this reaction go to completion. In other words, you want to use up all of your reactants because you have a limited amount of that, and you want to make the max amount of products. So the way to do that is to remove products as they're made. So when we do that, let's go look at how we do that. When we remove products, we're going to make this side lighter, right? We're going to make this side lighter. We're pulling it away. And then, so what then happens is when we pull stuff away, we're going to shift the equilibrium so that we're taking some of the reactants and converting them now back into products to replace the products that we're removing. So when we take, the reaction shifts towards. When we take, the equilibrium shifts towards. We could do the same thing over here. When we go on this side, if we take reactants away, for whatever reason, the shift is going to be towards the reactant side. So we take, it's towards, take, towards. Opposite of the other one, right? We take away, it's going to be, the reaction is going to shift to the side we're taking it away. So here's another quick demonstration of what I mean by this. So let's look at this this system here, where it's just two containers of water that are held together by a tube that connects both containers of water. And if you've ever seen this done, if you pour water into one of the containers, it will fill up the other container until the heights are level. In other words, the height of one side is going to be equal to the height of the other side. And that would be called equilibrium. So let's show that over here. Right, that's right here, equilibrium. The heights of the water on each side are the same. Now let's say we add water to this side here. So let's do that. We're adding water to this side. It's like we're adding it to the reactant side. So we've done that. And now what happens? So when we add water, the excess water is going to come shoot over here and here until we go back into equilibrium. The water is going to come back over here. The pressure on this side is going to push it over here until the pressures of the columns of water are going to be equal in height. Right, so now the height is a little bit more higher than when we started with because we've added some material to the system. But at the end of when equilibrium is reached again, the two heights of the containers are going to be the same. Now let's say in this case here we're going to remove material. We're going to remove material. And so what happens then, again, is that the extra water over here is going to come back and repopulate this side of the container until we're back at equilibrium. So again, add away, take towards. Okay, so now a couple of other things. Let's look at a real bona fide reaction here. We have, let's say here, we have nitrogen gas, which is here, nitrogen gas, and we're going to add that to 3 moles of hydrogen gas. So we have 1 mole of nitrogen gas, 3 moles of hydrogen gas. This is in equilibrium, so there's a forward reaction and a reverse reaction, and we're going to make 2 moles of ammonia gas. So 1 mole of this, 3 moles of this gives me 2 moles of this. And we also generate this thing, we also generate some heat. All right? So let's see what happens when we upset the balance of this by adding or subtracting, putting a stress on the system. So let's look at here. Here's my first stress. Okay? I'm going to increase the concentration of a substance. So let's just do this for giggles and grin. We're going to add a little bit more nitrogen on here. And what does my thing say? My thing says that my shift is going to be away from the substance. Right? So that means my shift is going to go to this side. So I'm going to shift it to the right in that case. Shifting to the right. So if I increase this concentration of substance, I'm shifting away. In this case, I'm shifting from nitrogen to the products, and that means that I'm shifting to the right. All right, so there's that. Now let's say we want to also do another one here. We're going to decrease the concentration of substance. All right, so let's look at that here. Let's say we're going to take away H2. And what does it say here? It says here that when we do that, we decrease the concentration of substance. We're going to shift towards the substance. Again, so now we're coming towards this side. So we're going to break down some of the ammonia back into H2 that we're pulling away. And so the shift is going to be back towards the thing that we're removing. Because we need to produce more substance to make up for what was removed. Right? And the top one, we need to get rid of the extra concentration, has to be used up. So the only way to do that one would have been move it to this side. All right? So far, so good. So right now, let's look at some other things that we haven't talked about yet. And this only applies to gases. Right? Increasing the pressure. So let's look at increasing the pressure here. So we're going to increase the pressure of the system. Well, you don't just increase it to one side or the other, you increase it to the whole system. But what it's saying here is the shift is towards the fewer moles of gas. right? So if we increase the pressure, increasing the pressure, so let's do that. We're going to increase the pressure through the whole system. So increasing the pressure here and increasing the pressure here. What it's saying is that when we do that, pressure increase means that there's a volume decrease, right? So if there's a pressure increase, the volume decreases. So it's going to shift towards the thing that has the lowest volume, which is the 2 moles of ammonia gas. Remember, we have 4 moles over here, 1 mole here, 3 moles here, but there's only 2 moles here. So this is going to take up less room. This is going to take up more room than this. So we want to get it back to something that has a lower volume. All right, and now the other side is when we flip it and we take away pressure, the pressure goes up, therefore the volume must go, if the pressure goes down because we're removing material, the pressure going down, we're going to have to increase the volume, and the only way to do that in this case is to increase the number of moles of gas, and therefore you're going to go back from 2 to 4, right? Increase the pressure, you're going to shift towards the side that has the fewer moles of gas. Decrease the pressure, you're going to shift towards the side that has the more moles of gas. If the number of moles of gas is equal in each side, there is no shift. If the number of moles of gas on each side is equal, the pressure has no effect on the shift. If you even increase it or decrease it, it doesn't have any effect because there's the same number of moles of gas on each side. All right? Now let's look at one more quick thing here that we haven't talked about yet, and that's basically temperature. All right? And in this case, temperature is going to be represented by this thing called heat. Remember, heat, when we increase the temperature, we're increasing the heat quantity of something. So if we increase the temperature of a system, we're always going to move away from the heat, right? So here we go. If we increase the temperature and the heat is on the product side, we are going to shift away from where we're adding the temperature. So let's look at that here. If we add heat, we're adding heat here, we're going to be shifting towards the reactant side. Add heat to an exothermic reaction, the shift is towards the reactants. Add heat to a reaction that is exothermic, you're going to shift towards the reactants. Now let's just say that the heat was on the opposite side for right now, just for the giggles and grins. So let's put the heat over here, okay? And we'll cross out this heat for right now. That's not where it is, but the heat is now on the reactant side. So if we add more heat or temperature, increase the temperature, again, we're going to shift away, so we are going to make more products. Adding heat to this side and putting temperature on and the heat's on this side, we're going to shift away. All right? So what you have to now know and understand is you're always going to shift away from the stress when you add stress. So in other words, if you're adding something to the reactant side, you're going to shift towards the product side. If you're adding something towards the product side, you're going to shift towards the reactant side. If you have a heat term and you add temperature, you're going to shift away from where you're adding the heat. So in other words, if it's an exothermic reaction, in other words, we're generating heat, so therefore it's in the products. If we increase the temperature, we're going to shift back towards the products. If it's an endothermic reaction, so we have to add heat to get the reaction to go, then if we increase the temperature, the shift is going to be towards the products, right? Shift is going to be away from what we're adding. If we take temperature away from an exothermic reaction, we're going to shift towards the products, right? The heat term is on the product side of an exothermic reaction. So if we take that away, just to treat it like a normal product, we take that away, we're going to shift towards it. Take away, towards. Add, away. It's that simple. The last thing we have to make sure we understand is the catalyst. The catalyst is fairly straightforward. If we add a catalyst, there is no shift no matter which way you go. Right? Add as much catalyst as you want because it just affects the rate of forward and reverse reactions the same. So if it affects everything the same, there's no shift in equilibrium.